Hello everyone. In this video we're going to continue our discussion of probability theory. We're going to take a look at expected value and expected value of sums, and all of these involve discrete random variables. My name is Professor Fred Rispoli. So we'll take a look at 4 different examples. 2 of these are from chapter 10 and 2 of these are from chapter 11. And all of these have a slightly different approach to finding expected value. So for the first one, let's consider a situation where a sports team loses 10 fans every time they lose and gains 100 fans every time they win a game. They have a 30% chance of losing, and their performance in each game is independent of prior games. What's the expected value of X, the number of fans they'll gain or lose over the next 3 games? So to find the expectation of X, we need a probability distribution, right? We need a table for the 3-game period. Remember, fans gained is found using a loss results in minus 10 fans, a win results in plus 100 fans. Probabilities rely on the independence, so we can create a table that looks like this. Think of the outcomes. You could lose all 3, lose 2, lose 1, lose 0, which is the same as winning all 3. If they lose all 3 games, they would lose 10 fans each game, so a total of 30. If they lose 2 games, well, they win 1, so they would gain 100, but then lose 20 fans because of the 2 games they lost. So their net would be 80. When they lose just 1 game, well, they would win over 200 fans, but then lose 10, so a net of 190. And losing 0 games means they win all 3, so a net of 300. Now the probability of losing all 3 games, remember they lose with probability 30%, so this would be 0.3 cubed. The probability of losing 2 games would be 3 times 0.3 squared times 0.07. The thinking is here, they're going to lose 2, so that probability would be 0.3 squared and win 1. But they might win the first, they might win the second, they might win the third. So this is a 3, or if you want to start to generalize, it would be a 3, choose 1. Okay, this is similar, but now they're just losing 1 and winning 2. Okay, here they win all 3, and you might recognize this as a binomial distribution. So to get the expected value, well, what we have to do is start looking at these products. So minus 30 times 0.3 cubed plus 80 times this probability and so on. And if we work it out, round it off, we will get 201. So that is the expectation. So again, you might find some shortcuts, but this is basically a binomial distribution problem. Okay, let's take a look at, well, a butterflies problem. You'll see these throughout our textbook, but this will raise a key idea comes out of this problem. So you might think it's simple, but it's important to understand this because there's a key solution technique that gets used throughout the textbook. So let's say Alice, Bob, and Charlotte are looking for butterflies. They look in 3 separate parts of a field, so their probabilities of success do not affect each other. In other words, they're independent. Let's say Alice finds 1 butterfly with probability 17% and otherwise 0 butterflies. Bob finds 1 with probability 25%, otherwise does not find one. And Charlotte finds one butterfly with probability 45%, otherwise does not find one. So here's the key problem-solving idea. Let's let x be the sum of 3 indicator variables. Now, indicator variables are sort of binary, 0, 1 variables. Usually, the xi is 1 if something is present. Otherwise, it's 0. So here we use these to indicate whether Alice, Bob, or Charlotte found a butterfly. So then we let x be the sum of these xi's. So it's sort of like you're breaking down the problem into cases. Each one of these cases are pretty easy to work on, and then we could add these up to find e of x. So let's consider the expected value for Alice, which is e of x1. So she finds one butterfly with probability 0.17, and she finds none. Now this probability has to be the complement, 0.83, but we don't need it, but it's just there. So e of x1 is 0.17, and similarly we get e of x2, 0.25, e of x3 is 0.45. So now we want e of x. We break x down into x1 plus x2 plus x3. But guess what? The expected value of a sum is the sum of the expected values. So we could just add these up. And part of the lesson here is this in red, what I just said. Expected value of the sum is the sum of the expected values. So that's why these indicator variables are such a useful idea when it comes to finding expected value in some complicated situations. It's also a good problem-solving tool in many other problems. So it's good to get comfortable with this idea. Okay, here's another expected value problem. Approach is sort of totally different from what we just did. This is a Chapter 11 problem. Let's start off. Consider a group of 120 students. Let's say that they need to be split into 2 lectures, 60 students per lecture. So I could have tried to represent this visually down here. This is lecture 1, let's say, and lecture 2. Then the same 120 students are split into 6 labs with 20 students each. Okay? And all assignments of students to lectures and labs, they're all equally likely. We could really think of this as random assignments. So this second level here, these represent the 6 labs of 20 each. The question is, how many classmates does Barry expect to be in both his lecture and in his lab? Okay, so it's an expectation problem, and let's do this. Here's another problem-solving trick. This is more of something you may do when you start to write proofs, but here's a famous phrase when you're doing proofs. Without loss of generality, let's suppose that Barry is in lecture 1 and lab 1. So let's suppose he's in this group and in this group. It doesn't really matter. It's the same reasoning, but let's just make it easy and think of lecture 1 and lab 1. So what's the probability of that happening? Well, when you have random assignments, the probability that a student is in lecture 1, right? There's only 2 lectures, well, that would be a half. The probability he's in lab 1, right? There's 6 labs, so that would be a sixth. All of this is independent, so the probability that just a randomly selected student is in lecture 1, lab 1 is 1/12. Now, we need to apply this we know there's 120 students, so we expect that 112 times 120, which is 10, are in both Barry's lab and Barry's lecture. But that 10 would include Barry. So Barry could expect 9 of the students to be in both his lecture and his lab. Okay, so that is example 3. Now in our last problem, we're going to take a look at another problem that's somewhat is different from the first few. This is different in the sense that we end up with an infinite sum. Okay, so let's take a look at this problem. Suppose that a student rolls a die until the first 4 appears. Let's let x be the number of rolls required until and including the first 4. After that part of the process is completed, he begins rolling again until he gets a 3. So x, again, is the number of rolls required until the first 4, and then once he's done getting the first 4, we count the number of rolls until he gets a 3. And we let y be the number of rolls until he gets his 3, but this is after the first 4. So some examples. Let's say here is our sequence of rolls. All right, so we sort of ignore that that's a 3 with respect to the y part. So the value for x is 8. Right? It takes 2, 4, 6, 8 rolls to get the first 4. And then after that, it takes 2, 4, 6. It takes 7 rolls to get the first 3. Right? We don't count anything over here. Let's check that out again. Let's say this is our sequence. It takes 4 rolls to get the first 4. And then after that, you can see we have 2, 4, 6, 8, 9 rolls to get the first 3 after the first 4. So we get 9. Okay. So it's important to understand that. I'll give you a couple more examples to sort of try to see if you follow this. That'll be part of the problem. Let's let AJ be the event containing all outcomes in which J rolls are required to get the first 4. Okay, let's let XJ be an indicator for AJ, and let's let this capital X be the sum of these indicator variables. No limit on top. So here's where we start to see, an infinite sum. So we want to do a few things. I mean, in general, we want to find the expected value of x by finding the value of the sum of the indicator variables. Okay, that's sort of the main problem. But I'm sort of breaking that down just so that it's a little easier to understand this problem. So the first thing that I want you to do is to figure out x and y for this sequence of rolls, and then find the probability of A2. Okay, so good chance to maybe stop the video right here, and let's see if you get parts A and B. Okay, so again, before going on, let's see how you did. So for part A, you see we get 3, 5 in the first case, right? The first 4 is here after 3. And then after that, the first 3 takes 5 rolls. For 3, the extreme case would be 1 and 1. And then in this case here, the first 4 occurs after 6 rolls, and then after that, the first 3 take 1, 2, 3, 4 rolls. Aha! Always something. All right, so this should be, what? Should this be a 5? No, that should be a 4. Somewhere I think I lost a digit, but that's okay. So this should be a 4. Okay, now, next we want to find the probability of A2. So remember, A2 is the event that it takes 2 rolls to find the first 4. So what's in A2? Let's just try to list the elements, right? We could have 1, 4, 2, 4, 3, 4, 5, 4, and 6, 4. So we have five values. And the set of all sequences, right, 2-row sequences with a 4 in the second place includes everything in A2 plus 4, 4. Okay, so one way to see this is we get the probability of A2 is going to be 5, 6, right? There's sort of 5 possibilities for the first digit. Add a 6 if you want, so we get 5, 6. Okay, so that's the way I want you to sort of think about this. That should help us for part C and D. So in part C, we want to find the expected value of x by finding the expected value of the sum of the indicator random variables. And then what can we say about the expected value of y? All right, so let's go on. So the probability of AJ in general is 5, 6 to the power j minus 1. Okay, because in AJ it's going to take j rolls to get the first 4, which means you have to have j minus 1 rolls that are not a 4. Okay, so what's the probability when you toss a die of not getting a 4? It's 5, 6, but this has to happen j minus 1 times. So we get 5, 6 to the power j minus 1. Now, once again, sort of like with the butterfly problem, because xj is an indicator variable, e of xj is going to be 1 times the probability of aj, which is 5, 6 to the j minus 1, plus 0, and we really don't care what this is. You know, I said it was just the complement here, 1 minus this, but we really don't care, so we're not going to, you know, spend any more energy on this. So we get 5, 6 to the j minus 1. All right, we're almost there. Now, we know that e of x is the sum of probabilities that look like this. So, sum from j equals 1 to infinity, 5, 6 to the j minus 1. All right, we could change this around a little bit and rewrite this as the sum. J goes from 0 to infinity of 5, 6. Why do you want to do that? Because now we have this as a geometric series. Okay, and we know there's a nice formula for geometric series, 1 over 1 minus sort of the base term. You might know this as A in a lot of formulas for sums of geometric series. So 1 over 1 minus 5, 6. Well, in the denominator, this would end up being 1/6, and 1 over 1/6 is 6. And there you have it. That is the expectation of x. Okay, and if we wanted to find e of y, it's basically the same reasoning as in part C. So E of Y turns out to be 6 as well. Okay, so thanks for watching the video. That's the end. You've been a great audience.